All right, thanks everyone. Pooya here to talk about constant cost communication.
Hi everyone, thanks for coming to my talk. Yeah, so I'm going to talk about constant cost communication. And some of the stuff that I'll talk about are based on kind of various recent joint works with subsets of this name. So Yuting Fang is my PhD student, Mika Göös, Lianna Hambardzumyan, Nathaniel Harms, and Hamed, who's here. And kind of the general moral of the story will be that we want to try to understand problems that have very efficient, very efficient communication protocols, and I will try to convince you that this is interesting. Right? So this already off the bat, it looks like way too restrictive, so why should we care about? And kind of, so if you are in communication complexity field, so you've, at least for many years, we've studied communication complexity motivated by the fact that you saw in the previous talk that it helps you prove lower bounds. So many algorithmic settings, you can kind of embed or discover a communication problem inside it by like finding some communication bottleneck and then proving very good lower bounds for these communication problems that you find helps you prove lower bounds in like streaming algorithms, data structure problems, all sorts of settings. Because of this, we've developed all sorts of lower bounding methods, or trying to find like explicit problems that are really hard, communication problems that are really hard, and kind of to exactly compute, or at least asymptotically compute, what's the best way to solve these things. And so the stuff that I'm going to talk about today are stuff that kind of has been a little bit under the radar, or people didn't care about it, or maybe it didn't seem interesting. So it's not truly honest. Of course, it's been studied a little bit. But kind of interestingly, in the last few years, there's been some development, some of this from my joint works, but generally in the community, there's been some interesting developments, and we've realized that, in fact, many of the tools that we've developed don't help answer some interesting open problems that come up. So I kind of will give you some interesting open problems, hopefully, that I hope that at least some of them are of analytic flavor. I kind of hinted at when I mentioned that some open problems in the open problem session, so they're going to be related to stuff that comes up in this talk. And yeah, so kind of, this is a computer science talk, so there won't be a lot of like analysis, but I will throw in some analytic, some of the results are proved from with analytic techniques. And some of the more recent stuff is combinatorial, but I'm hoping that the improvements of them will have analytic flavor. So it's like communication, it's a talk about communication complexity, so let's just start by really formally defining, or somewhat formally defining what's a communication problem. So a communication problem is defined by some Boolean matrix by some matrix like n 0, 1 to the n by n. So you can think of, we are given this matrix F, and it has like some places it's 1. And we think of two, so this is the most basic model that we're going to study. So we have two players, Alice and Bob. Alice is given a row X, Bob is given a row Y, and what they want to find out is whether this entry is kind of, so what they want to find out is if that entry is a 1 or a 0. So both of them want to do this. So what can they do? So Alice only knows her input, and Bob knows his input, and In the most basic model of deterministic communication, they take rounds, they talk to each other, so they ahead of time know what the matrix F is, and they can decide a strategy, so they can agree on a protocol ahead of time of, okay, so if I see this particular vector, I'm going to send a 0 first. If I see, so Bob knows what Alice's strategy is, but Bob doesn't know Alice's input. Okay. So this is the deterministic model, which is kind of very restrictive, but even understanding efficient deterministic protocols is interesting, and there are some major open problems such as the log-rank conjecture here, so I will talk about that a little bit. But you can make this protocol more powerful by kind of giving more power, by allowing the players to toss a coin. So that will be very key to our talk. So we can make this randomized. And in fact, we will just mostly, this is the model that I'm talking about. It's a public key randomness where you can think of there's this blackboard that Alice and Bob both see, and kind of they can access both a shared random string of any length that they want. So their protocol is randomized. Okay. So this seems more powerful, and indeed it is. And let's gain some intuition. So I'm going to spend a significant amount of time of going through important examples so that we can actually come up with some open problems ourselves together. And we also gain some intuitions of what efficient randomized protocols looks like. Okay, and also feel free to stop me if there's any questions or something is unclear.
So you say the communication problem is defined by the matrix.
Exactly. Yeah.
And what is the problem?
So the talk is about trying to generally understand, so like what communication problems. So I'm going to define now a bunch of specific communication problems.
Okay, so you didn't finish it.
Yes, so this is just, like if you fix the matrix F, let's say F is the identity matrix, F is like a certain type of matrix, then you can try to understand what is the best protocol for such problem. Right? So this like the identity is a family of like matrices of growing size, and then you can try to see like how the number of bits that need to be communicated to solve it, like how does it depend on the size of the matrix is what people say.
Okay. So when you say that randomized communication is more powerful, you mean there is a separation, or you just mean that in general it could help?
Yes, so let's see. Yeah, let's see in a second. So all good questions, and we will see. So let's focus on deterministic for a second, and we will see the advantage of randomized. So just to have an intuition of how a deterministic protocol would look like, let's assume F has rank 1. So F is rank 1. Okay. So what is the communication complexity of this problem? So how many bits do you think Alice and Bob do you have to talk to each other in order to compute f of xy, right? So Alice has x, Bob has y, and they want to know what is f xy. Okay, so any suggestions? 1. Yes, so 1 or 2 based on like how you define your model. So one thing that I didn't say, so when do we stop? We could stop if both Alice and Bob know the output, or we could stop if just one of them finds out the output. So this is 1, and so what is the protocol?
You just take inner product next with this rank 1 stuff and a form.
Yeah, so what does a rank 1 matrix look like, right? The 0, 1 matrix look like? It's just like 1 somewhere. So there's a non-zero row that repeats up to permutation. This is what it looks like. And what Alice can tell Bob is just a 0, 1 bit. We're saying like, if this is the set of the 1 rows of Alice, then Alice will send, I guess, to Bob whether X is in S or not. And now Bob immediately knows that Alice's input is one of these rows or not one of these rows. So if it's not, then Bob already knows that the output is 0. But if it is, then Bob can just check whether y is one of the columns of this rectangle, which tells you what the output should be. So in 2 bits of communication or 1 bit of communication. So this has a very efficient protocol, even in the deterministic setting. And this, it turns out that the rank 1 is not, I mean, this generalizes. So even if so for rank R matrices, there is a deterministic protocol that communicates R bit. Okay, so you can think about this. So if you have a rank R matrix, the number of distinct rows is at most 2 to the R. So Alice can just tell Bob which of the distinct rows does she have, and all we need to know is like what type of row Alice knows. So Bob can actually look up what the value is. Okay, and you can even go back. So in fact, if you don't care about the relationship between the rank and deterministic communication complexity, rank really captures having constant, like if you care about problems that have constant cost deterministic protocols, rank indeed captures it. So because we can show that if D kind of denotes the deterministic communication complexity of the matrix, then we know that D is at most R. And if you kind of inspect what a protocol's leaves look like, then that also gives you a lower bound of log of R on your deterministic communication complexity. And the famous log rank conjecture claims that this R can be replaced by polylog R. Okay. And widely open, and I don't know if, I mean, some people believe this conjecture or not, but yes, for every example that we know, it's true. Yeah.
So the conjecture for two-way or one-way?
Two-way. Yeah.
One-way protocol.
It's for two-way, yeah.
And for one-way, like, do we also believe it's true? Or?
I don't think, I'm not sure. Do you know? I don't know, yeah. But so one thing that we know is that square roots are, like roughly square root R is now known. But that's the best, and we know that if you want to prove this conjecture, the power of log has to be at least 2. There are separations of the quadratic. There are in fact matrices that require this square.
This is still in deterministic setting, right?
Yeah, for now it's deterministic. Yeah, exactly. But let's move on to a very
I don't understand what in this simplest case Alice communicates to Bob.
So Alice tells Bob 1 if Alice's row belongs to one of these.
But she doesn't know where is S.
Oh, Alice knows X.
F is no what.
Huh?
Alice and Bob both know F.
Ah, they know it.
They know F, yeah. So they know the problem they want to solve, but each of them has half of the inputs that they want to.
So what is the goal of Alice and Bob?
To find out F of xy.
To find out the value. Okay.
Yeah. So think of in classical complexity, you want to compute an F on an input. And now we have split the input into 2 parts, and each party has only half of the input.
And what is one way?
So one way means that the communication goes only from left to right, and the goal is that Bob just finds out the answer. Yeah. So like Alice will never find out anything about Bob's input.
I think that might not be true for one way because you have asymmetry. Like for example, you want to compute the address function. Like Alice has an n-bit string and Bob has an index. If you send from Alice to Bob, then it's like you need to send everything. But the rank is if you do the other way, then it's just log n bits.
I see. Yeah. So it's exponential. Yeah. So you just need the full. Okay. Good. Okay, so now let's look at If you care about randomized communication, one of the most important examples is the equality problem. So the equality problem is defined whereby the matrix where the entry of xy is 1 if x is equal to 1. So this is 1 if x is equal to y, 0 other way. And so obviously, so this is the identity matrix. This is the n by n identity matrix. So, so equality of xy is just EQ is just the identity and vertices. So you have and rows and columns. So you have these. And we just want to see if we are on the diagonal or not. Okay. So how many bits does a deterministic protocol need to communicate? Log n. So you actually, if you believe what I said here, or it's just one of the first exercises in communication complexity is to prove that, the leaves of any communication protocol correspond to kind of sub-matrices, and the function has to be constant on those, and none of these elements on the row can be in the same sub-matrix. So they all have to be different leaves of the protocol. So you have n of them, so deterministically log of n. And this is as bad as it gets, because any problem has a protocol that communicates log of n, but you just tell Bob, it's one-way protocol, so Alice just tells Bob the row, the name of the row. But what about randomized? Can we do better?
You just XOR with random vector or something.
XOR with random vectors? Yeah, or like a hash. Yeah, exactly. So or with two random vectors or something. Yeah, or another way to think of that protocol is to kind of Alice and Bob use the public randomness to use randomness to take random, like lowercase, let's call it labeling, so L from n to 0, 1 squared. So this gives the same label to every row and its corresponding column. So each row is now labeled with some random string. And the same column, so something like this. And what Alice and Bob will do is they will just check if their inputs are mapped to the same vector, right? So the protocol is that Alice sends to Bob L of x, and then Bob checks if L of x is equal to L of 1. So if x and y are different, then the probability that this protocol detects that they're different is at least 3/4. And if they're equal, this protocol will just never say that they were unequal, right? So if x is equal to y, then they're always hashed into the same string. Okay, so 2 bits of communication suffices, or all one.
So you're assuming error in one pair is the definition of randomness.
Exactly. So the error problem. So I should have mentioned. So when we introduce randomness to communication complexity, you have to allow error to make this interesting. If you're still making sure that it's always you have to give the right answer, that doesn't help you. So we will just require protocols to give the right answer with probability at least 2/3. And that 2/3 is arbitrary. Any number bigger than half would have worked because you can repeat the protocol, take majority, things like that. So what this shows is that randomized cost is all 1, but deterministic is greater than or equal to log n, which was as bad as it gets. Right? This is something that's very rare in complexity theory. You get the most dramatic separation in communication complexity, advantage of randomness. Okay, so and because of this, equality is a very important example. Okay. So are there other examples that have such dramatic situations? So in this talk, I'm going to focus on trying to understand what problems are like equality. Okay. Okay, so natural question. Have for 1 cost randomized protocol. And I mean, this seems very restrictive, so it's and I think because of this it wasn't as well studied, but interestingly, when you try to study it, you see that many of the techniques that we've developed fail to answer questions that arise. And it's kind of a lot of interesting mathematical questions arise that I want to motivate in this talk. The challenges some challenges of studying this are not many examples are known. Which kind of justifies maybe that's like, that's why people thought it's uninteresting, right? So we don't have, we have just a handful of examples that have this hyper-efficient, so this dimension-independent protocols in the randomized model, so maybe it's just not interesting. But there are some kind of reasons that you might want to study this model. It's for example, if you're familiar with the private coin model where Alice and Bob have access to private coins, then this model distinguishes between those two. So no longer you can say private and public randomness are equivalent because, for example, the identity, you can also show that in the private coin model, it has to have a dependence on the dimension of the matrix. Okay? So in order to gain some intuition about these problems, let me tell you some more examples that have such problems, and let us actually come up with protocols. So the next one is the tree adjacency problem. Okay. So in this case, now I'm going to assume that the matrix F is the adjacency matrix of a tree. Okay. Of a tree. T. So we think of, so we have just some tree. And then we don't know what's going on here. So Alice is given X, Bob is given Y, and they want to know whether there's an edge between X and Y. Okay. So this is again an n by n matrix where n is the number of vertices. So what do you think the randomized communication complexity of this problem is?
Should be close. Should be like that.
Why? It's a very good observation. So we've established that this has an efficient protocol, so we can try to use that protocol. So one very useful thing when you're given a tree to do is to make it rooted. Okay. Yeah.
I was just going to suggest you could, Alice could walk. We don't know anything about the like degree of the vertices, right?
No, we don't have any guarantees on that.
Maybe if you're rooted, Alice could say in which subtree on like level 5 trees or something.
So let's think about the rooted setting. So because Alice and Bob know the tree, so they can agree on a root ahead of time. So they will pick a root, and then they both have access to now the rooted version of that tree. And now Alice has X and Bob has Y, and they want to know whether they're neighbors. If two things are neighbors, one has to be the parent of the other. Okay, so with two queries to the equality problem, you can check. So Alice, so the protocol will be the following. So Alice kind of sends like I guess that's why I want to make to write Alice. So all they have to check is that is X equal to parent of Y, and then is Y equal to parent of X. Okay. So we didn't have to come up with a fresh protocol of hashing or anything, we just did two of these protocols. And of course this reduces increases your error probability. But you could repeat this protocol and make sure its error probability is small, so that when you do a union bound here, you still are below 1/3. Okay.
They need to fix the R beforehand, right? Or
Yes, exactly.
Okay.
But
doesn't
so
count
they
as
get to
a
design the protocol based on the problem that they want to solve. So the problem is given to them, which is the tree's adjacency matrix.
Yeah, but like they need to communicate in advance which R will
Exactly.
be. Okay.
Yeah. Yes. So there's so communication protocols are designed based on the problem. So that can be inside the description of the protocol. So for this problem, we pick this route.
How do you check fast if X is parent of one? Or
Well, so Bob knows Y and P of Y, and Alice knows X and P of X. So in the first round, they will just check whether X is equal to P of Y by just running the equality protocol, where now we think of the columns as P of different Ys. Yeah. So this also has an O1 randomized. Okay. Sorry?
What if it's direct product of two rooted trees?
The direct product of two rooted trees. Maybe it has also an efficient protocol. Yes, it probably
There
has.
can be several parents,
Yeah.
but still okay.
Not sure. But yeah, so we can think about that.
There can be two parents.
Okay. Yeah, so we can. Yeah, so let's. So we can do that type of generalization, or let's look at the completely different problem now. But so this is the kind of the direction that literature has taken, and in fact many examples that we know are graph problems. So they're graph adjacency problems, or deciding whether there's a constant distant path between two vertices in some large family of graphs, like bounding different things like twin width of the family or other types of things. But so let's look at another type of graphs and trees. So assume now so that we have planar graph adjacency. So now the question is clear. So there's some planar graph G instead of a tree that is given to both Alice and Bob, and they just want to see again. So is xy in P of P, where P is a planar graph. So what is the most efficient randomized protocol for this? Or is there an efficient randomized protocol for this?
it?
To forests, yeah. So every planar graph can be decomposed as like, it can be partitioned into 3 forests. So the protocol, so ahead of time, so they kind of partition P into 3 forests, and then solve adjacency in all the forests.
Is that bit why you have 3 forests?
So you can use Euler's theorem that shows that there's a degree at most 3 vertex, and then you can inductively kind of, so do that, right? And in fact, so this also, so first ahead of time they agree on a partition into 3 forests, and that you can observe that this protocol generalizes to forests, so they can for every connected component pick a root, and just the same protocol would work. And the fact that we solve this using equality, that means that we can solve this using a bunch of equality queries. Okay. So you can see a theme here so far. So we are trying to come up with new problems, but we keep this thing, encountering equality. And in fact, so this observation, so all we used here was the fact that there was this family of graphs had this low degree vertex. So in general, so this observation shows that bounded arboricity or bounded degeneracy graphs also will have constant cost protocols because they can always be decomposed into a bounded number of forests. But let's look at an interesting generalization of equality. So let's think of equality now as, instead of just taking n numbers, so let's think of n as 2 to the n. So you can think of the equality problem as Alice is given an n-bit string, lowercase n-bit string, and Bob is given lowercase n-bit string. And what we want is the equality of xy is just the indicator of whether the Hamming distance between x and y is 0, right? So if we think of this matrix as like a 0, 1 to the n by 0, 1 to the n. Okay? And this observation allows you to try to generalize. So what if we ask about other Hamming distances? So the one Hamming distance problem is simply, so we denote it by 1HT. 1HT of 2 n-bit strings is just the indicator of whether the Hamming distance of x and y is equal to 1. So kind of Alice has x, which is this n-bit string, 0, 0, dot, maybe a 0 here, and y. They want to see if the number of bits that they're different is exactly 1. Okay? So what do you think the randomized communication complexity of this problem is? So this is at least as hard as, first of all, solving equality, because you can solve equality by just like putting a 0 and a 1 at the end of any string. If they were equal to begin with, then their Hamming distance is exactly 1. So this is at least as hard as that. But is it much harder? It is not. So what is the protocol for this?
Maybe just can hash by XOR increase 0, 1, but modulo 10, and then look if the answer is different only by 1, something like this. So you sum subset of the bits and take the answer modulo 10.
Yeah, so even modulo 2 will, okay, so that I think that works. Yeah, exactly. So I think that works. And another thing that we can do that might simplify our life is to use equality. Okay. So I mean, that's what you said is kind of trying to solve it in one shot, and I think that works. So what we can do is another randomized protocol that kind of is nice to write down is first like check equality. Right? If they're equal, then we're done. So that's great. Okay. And if they're not equal, now we want to see if there is one or more coordinates. So then we just pick some subset of the coordinates uniformly at random, and then just check if both S and S complement are unequal. Right? If they are, which they will be if they're having with some constant probability. So check if, I guess reject if EQ of X restricted to this and is equal to 0, and also EQ of XS complement and YS complement is 0. And then you can see that, well, if there was only one, so only one of the sides will always be equal. And if the Hamming distance was more than one, this will always detect it with some constant probability, so you can boost also the error by repeating this protocol. Okay. So this kind of, but the difference is that this is a randomized protocol as compared to our algorithms for planar and tree adjacency were deterministic protocols that used equality. So in the end, they were randomized because we solve equality with randomness. There's a bit of a difference between this protocol and the other reductions to equality that we said. Okay, and it's important for this talk. So here we use some extra randomness before even using equality to solve. So we pick the random subset. And so this also has an O1 randomized protocol.
And if our characteristic function where distance is less or equal than 1, same thing?
Yeah, so less than or equal to 1, then it's kind of simpler, so then we just don't need to do this part. Yeah. But it's not much harder, so they do reduce to each other. And in fact, you can generalize that one Hamming distance to k Hamming distance when k is a constant, and people have even tried to optimize what is the exact randomized communication complexity. So we actually know that for k Hamming distance, it's actually theta of k log k if you fix k. Okay. At least if k is not too large, so for k up to square root n or something, so this is the right, and this is by Salam from just a couple of years ago. It's not that trivial to find out this exact optimum solution. So finally, so let me give you one more generalization of Hamming distance that's going to be interesting to us, which is Hamming distance over large alphabet. So suppose we have just some alphabet, sigma. This is some large finite set, and we still want to solve. So the KHD sigma is something from now sigma to the n, right? Sigma to the n. 0, 1, and KHD sigma of xy is just the indicator of whether the Hamming distance between xy is k. Okay. So what is the randomized communication complexity of this problem?
Is sigma constant size or?
Yeah, so some bound, not constant. Can different, yeah, so that can grow. It's just finite.
That doesn't depend on n.
It can.
I guess if it's constant, you can reduce to binary.
What's that?
If the
Yeah, exactly. If it
constant
was
is
finite, you could reduce to binary. That's true. So a very interesting observation is that this is really this can be solved by regular Hamming distance. So it's an interesting.
And the source of randomness is the random stream. It's sigma n. This is what you have.
What's that?
You have the source of randomness, right?
Yes.
And what you have is a uniformly chosen string of.
No. So we want to solve it for every x and y, right? Yeah.
But randomness doesn't matter whether it's random bits or random sigma elements, right? You can like mimic random elements of sigma by random bits. Because you have infinite randomness.
You need to have longer one. And
you have infinite randomness always.
Okay, infinite randomness.
So I mean, I guess so. There's two ways to see why this has a constant cost protocol. So something that only depends on k. So the first thing is that our solution to k-Hamming distance just squares to equality. Equality doesn't care about the alphabet, right? So even if you solve equality over sigma to the n, it's just it solves it for you. It doesn't care about the size of the matrix. Another interesting observation is that this is really just a two k-Hamming distance in disguise. So you can look at this, define an indicator code that maps sigma to like 0, 1 to the sigma, and just like you can say the indicator of x is ex. Okay? And what Alice and Bob can do is Alice just writes ex for every symbol, so e indicator of, let's say, some symbol, sigma, e sigma. So Alice will replace each of them by sigma, and now if the Hamming distance was k to begin with, now it becomes 2k. So just one 2k Hamming distance solves this. Okay. Does anyone have some suggestions or other type of problems that comes to your mind that might have constant cost? Okay, so my hope was no, because I claimed that we don't know anything else. Okay.
Do I understand correctly that the adjacency question for arbitrary graph gives arbitrary problems? Or not?
Exactly, yeah. So you can always think of the communication problems as just adjacency in some graph. Yes. So yeah, that's true. And you can have graphs like the adjacency of them is defined by set disjointness or something. So it's as hard as it gets.
So what's special about these specific graphs? I mean, they admit like really nice group actions. They're like very symmetric.
I mean, you tell me. Yes, that's the question. Yeah.
Okay.
What is what
You also said that the family of graphs has like bounded degree vertices, then the same thing.
Exactly. So there is a lot of works that try to come up with bigger and bigger families of graphs for which we can solve this, but none of them really just characterize. Right? Give us a character. Yeah.
This doesn't have bounded degrees. All this Hamming distance is not like that.
No. Yeah. So this one, it's very good observation. So these are not like the others in some sense, and that will be important. So this is all that we know, and this is kind of in quotation marks, in the sense that
Is there any notion of completeness here that
it's like two lines coming. Yeah. So this is all that we know in the sense that everything that we know provably reduces to what I've told you. Right? So, and what is a reduction? So we define the notion of reduction. So there is a notion of reduction everything reduces to some k Hamming distance. So every problem that we know that has a constant cost protocol, we actually prove in one of my recent papers that they basically reduce to some k Hamming distance. So even though there are all these works that have these complicated graph families, they all are just k Hamming distance queries in disgrace.
So,
Yeah.
when you say everything, you mean every exam, every known exam?
Yeah. So everything that we know. Yeah, sorry, thank you. New. So there's some, there's the point to this talk, actually, not just to some k Hamming distance. So what is the notion of reduction? It's kind of what we've been doing so far by kind of Alice sees x, Bob sees y, and they turn it into a new string and then query the other problem. So let me just write down the notion of reduction. Now I realize I should have given 2 talks. Underestimate 4 talks. Okay, so we say, so let's say P and Q are communication problems. And we say P reduces to Q if P can be solved deterministically with all 1 queries to the problem Q. So what is a single query? So we think of a single query as Alice has X, Bob has Y, and Alice maps her inputs to some other string A of X of some length. Bob maps it to some other string of a similar length, and then they ask the oracle Q of A of X and B of Y, and then they both see the answer. Yes, so that the reduction has to be deterministic. Yeah. Because if our reductions are randomized, then you just don't need Q, right? So if P already has a randomized protocol or Q has a randomized protocol. Yeah. So the same way, like in NP reductions, we do P, so polynomial time reductions. So that's
Do you know that Hamming distance is not reducible to equality?
yes. Yeah, we can prove that. Yeah. So, and that actually has an analytic proof, so we will see that in a second. And a few remarks about query protocols. So if you're familiar with query complexity, so it matters whether your queries are adaptive or non-adaptive. And it turns out here it doesn't matter because we're in the constant cost regime. So every adaptive protocol can be turned into a non-adaptive protocol because Alice just can send the entire tree's queries like to so they can just do all of the exponentially many queries, which is still a constant. So adaptivity doesn't matter.
So the maps A and B are injective, right?
Sorry?
The maps A.
No, they don't
Not
have to
necessarily.
be. No. Yeah. So you should think of, so this can be a much larger queue and we're just querying it on some subset.
A few of them.
Exactly. Yeah, so we can even do it. Yeah, you can even do repeated rows and stuff. Okay, so by this definition, what we've seen, so what we've shown is that equality basically reduces to planar adjacency reduces to forest adjacency, which reduces back to equality. And it's easy to see that equality reduces to 1 Hamming distance, which reduces to just 2 Hamming distance, and so on. Okay. And in fact, every other example that we knew of until recently reduces to something down here. Okay. So two natural questions. So one of them already asked by the audience is equality query all we need? If that's not true, and it is not, so this turns out to be no, is some AHD query all we know? And finally, is there any complete problem? For constant cost. And all of these are for constant cost. And the answers to all of these are no. And so this is a recent joint work with Yuting Fang, Mika Göös, Nathaniel Harms, and myself. This is 24 plus. And this is a joint work in stock this year. So this was Yuting Fang, Lianna Hambardzumyan, Nathaniel Harms, and myself. And this, there are multiple proofs of this. So there is, in a non-quantitative way, this was proved by Harms, Wiles, and Zamaraev in 23, and also in my paper with Lianna and Hamed in 23. Okay. And so interestingly, these two are very combinatorial. They use like hypergraph Ramsey theorem, etc. So that they give you terrible bounds. Or no bounds at all, that would matter. But this one is, our proof is analytic, so it gives you like a reasonable lower bound. Okay. And so these two, so these two are kind of stronger statements than the first one, but they're not comparable. So maybe I'll just hesitate there to see. So does anyone see why these two don't contradict each other, or like don't imply each other? So
can you explain the second statement?
So the second statement, so what you may wonder is that for every problem that you find that has a constant cost, there exists some k, such that p reduces to k having distance. But this hierarchy itself doesn't have a constant cost protocol, right? So they have even unbounded VC dimension as k goes to infinity. So this is kind of a very strong type of statement to try to prove. Nevertheless, that doesn't imply this one, because this is making an argument about you get to use as a query or oracle queries to some problem we don't know about.
Yeah, it's kind of like co-NP and NP, right? It's like you can have these hierarchies that are intersecting, but not every problem lies in, even if it were infinite, not every problem has to lie in this particular.
Exactly, yeah. So you have this infinite problem, hierarchy of k-Hamming distances, which actually follow from our result in the second part, the way we prove that.
Okay, but
not every problem has to reduce to that hierarchy.
Right, but the answers on here, they don't, it could be that every problem reduces to some KHD, is that?
But we say that it's not some. Yeah.
So problem 2 is asking.
Yeah, so what this implies is that there's no single k that everything reduces to it.
Right.
It actually proves more. It says that there is not even more things that have constant cost that something reduces to. Okay, so that's.
But in 3, I mean, your n is the parameter which changes. Then, I mean, when you say complete problem, it should be family of problems which grows with n, right?
Yes. Like equality or k-Hamming
sequence. There is no sequence of matrices.
Yes.
Okay, this is the statement.
Yes. Yeah. So a communication problem is a sequence, growing sequence of matrices, or just a family of matrices.
There is no complete.
That there's a dimension-free randomized protocol for them, and this whole family does not have that property. So that's what makes 2 different. Yeah.
Does it change if you change this reduction deterministic to randomized?
then everything, then you don't need the oracles kind of queries. Because you can already solve, so this is about problems that have constant cost proof. Okay. And something else that I didn't mention is that as soon as you start studying oracle protocols, then you don't need to talk about communication anymore, because as long as Q is non-trivial, then Alice and Bob can use queries to communicate bits, right? So Alice can just, if there's non-trivial rows and columns, they can just talk to each other by queries. Okay. Yeah. So this clean makes the model kind of clean. Okay.
Sorry, can I ask one more? Are there? Do you know yet whether there's like infinitely many incomparable the hierarchies of these things, or you just have?
So in this paper, we prove that the K-Hamming distance is indeed an infinite hierarchy.
Yeah.
So
sorry, infinitely many
large
distinct hierarchies. Like we have like NP, P to the NP, etc. We also have co-NP, co-NP to the P to the co-NP, etc. But there could be like more of these infinite hierarchies, none of which are.
At least we find a new infinite hierarchy when we.
So there could be like finitely many of these.
I'm not sure. I also don't follow the co-NP parallel, so I don't see what is co here.
Oh, not co in particular, just the fact that we have two hierarchies of reducibility that whose intersection is like not well understood and probably distinct. Sorry.
I see. Yeah, so we can think about that. Yeah.
Complete problem. What complete means?
Complete means every problem that has a constant cost reduces to that. Yeah. I mean, hard means that, but we want the problem also to have a constant cost. That's what otherwise, you can have problems like disjointness that have unbounded BC dimensions, so everything reduces to them with just one query. So the key difficulty here is that when we define oracle reductions, we don't bound how large Q can be. So even to solve n-bit problems, you can query Q on like 2 to the n by 2 to the n matrices, etc. So that kind of, these are powerful reductions that only make sense in the constant cost regime. Okay. So I don't think I will have time to tell you too much about these proofs, but let's see, like, even studying equality oracles leads to some interesting stuff. Understanding equality protocols. So we will try to take inspiration from the deterministic case. How did we understand deterministic constant cost protocols? We looked at the tree and realized that every query that you make either splits the rows into two subsets or splits the columns, so the leaves are matrices. So it probably is helpful to understand what does a single query to the equality look like. And so what does a single query to equality look like? It will label all of the rows of our matrix, our target matrix, with a bunch of strings, like A of like x1, A capital N, and then B1 up to Bn. And then we're just asking, is A1 equal to B1, A1 equal to B2? So that partition. So if it's 1, we go right. If it's 0, we go left. So a single equality oracle, after you permute, if you sort A1 up to An and B1 up to Bn, kind of partitions your matrix into something that looks like this. And so that's the right moving part of the tree, and then the left moving part is the unhighlighted one. Okay? And if you kind of step away, or like people in the back, it looks like an identity matrix that you've added some, so it looks like an identity matrix, and we call such matrices blocky matrices, and these matrices come up in other models, so they've been given various names, equality matrices, or like in graph theories, they've been given fat matching, so they have been studied before. But kind of a single query partitions your matrix to this highlighted ones and the unhighlighted parts. So this observation tells you that kind of the leaves of your matrix, like your communication protocol, are basically intersection of a bunch of blocky matrices and complements of a bunch of blocky matrices, because you're just moving through a protocol tree. So what this observation tells you is a theorem, kind of similar to the rank version, that if EQ, so if M constant cost reduces to EQ, then can be written as kind of plus minus sum of a bunch of blocky matrices. I goes from 1 up to some constant. You can prove this, but so like we already just proved it in in one. Okay, so I'm assuming M is plus 1 minus 1 matrix. Okay. And
or 0, 1, why do you need
so because it's like J minus B type thing, so you get the 0, 1. Okay, so I guess yes, that's true. Yeah. 0, 1 is okay. And this is similar to the rank type of idea. So our BIs were rank 1 matrices, now our BIs are blocky matrices. So we can actually define a new notion of rank and study this quantity.
Why it's plus 1 minus 1?
So if you look at this part, it's J minus a blocky matrix, and if you want to kind of write an expansion, so it's like the entry-wise product of J minus blocky times what happens on the left side of the protocol. So if you expand this, you get just a bunch of like minuses and pluses of intersections of like a bunch of blocky matrices, which is also a blocky matrix. So you get like this will be exponential in the depth of the protocol, but for us things are constant.
Those BIs could be the same, so that you have like integer values.
Yes.
Okay.
Yes. Yes. Yeah.
And every one of block matrix, every block is of rank 1 or?
Every block is of rank 1.
Of rank 1, right?
Yes, exactly. So it's so when you reach leaves, these have to be just 1 or zeros. Yeah. Okay, so you can define the blocky rank of M to be the minimum of like R, such that M is some linear combination of R blocky matrices. And what we've shown is that if M reduces to EQ, then it has to have bounded blocky rank, right? So if you want to prove a lower bound, if you want to prove something does not reduce to equality, you can prove a lower bound for this. But we don't know how to prove good lower bounds for blocky rank, unfortunately, at least if you wanted to prove really strong lower bounds. In fact, there is motivation to even take M that doesn't have constant cost protocols and prove exponential lower bounds, or the lower bounds are linear in the size, or polynomial in the size of the matrix. So there's motivation to prove lower bounds for blocky rank because of depth 2 circuits with exact threshold, of exact threshold. I won't get into details of that. So there's motivation from circuit lower bounds, so you can prove interesting stuff. But also where's the analysis? So we can turn this into an analytic notion, which we can define a blocky norm of a matrix to be the smallest sum of alpha I such that M is okay. So now I don't care about the number of blocky matrices that you use, I care about the sum of the absolute values of the coefficients that you use. Okay, so this is another notion. Yeah.
So you want exact equality, not like approximation by a blocky norm?
No, not yet. Yeah.
Okay.
Yeah. So this is just the blocky norm. Yeah. And if you look at this statement, not only it gives us a bound on the blocky rank, it also gives us a bound on the blocky norm because the coefficients are plus minus 1. Right? So this same theorem implies that the blocky normal M is O of 1. Okay, and also its blocky rank. So if you want to prove a matrix, if a communication problem does not reduce to equality, all you need to do is to prove that the blocky norm is not constant. It's just super constant. Okay, so how do you prove such things? So let me just give you that. I will have to just stop after. So the observation is that so we want to prove the theorem that one Hamming distance, or in fact any k Hamming distance, does not reduce to equality. And in order to prove this, by this observation of this theorem, all we need to know is to understand the blocky norm of this matrix. And then, so fact for XOR functions, where f of xy is defined by some Boolean function applied to f XOR y, it turns out that blocky norm is nothing so kind of excitingly new. So it's just for these functions, blocky norm so of f is just theta of the spectral norm of f, which is just the sum of the absolute values of the Fourier coefficients. Okay, so this goes through a bunch of reductions. So you first have to observe that this blocky rank is up to constant factors equivalent to the gamma 2 norm factorization norm, and or it's equivalent to the normalized trace norm, and the trace norm is for such matrices, the eigenvalues are exactly the Fourier coefficients of the matrix, the function that you lifted, and this function is an XOR function. Right? So the Hamming distance is just taking the XOR of two vectors and saying, is it the Hamming weight 1 or not? Okay. So just using this in my paper with Hamed and Lianna, we analyzed the Boolean function that is lifted to give this, and we showed that the kind of the one Hamming weight problem has spectral norm, which is kind of theta of n to the, I guess, so for k Hamming distance, we prove that this is kind of something like theta of n to the k, and this uses some kind of nice, it's kind of like an exercise. I just heard Hamed gave it as a homework to students.
Hyperactivities, you should have mentioned.
Okay, yeah, there you go. Yeah, so it uses like Kinchen inequality and so on. And this equivalence between blocky matrix to move to the spectral norm uses like Grothendieck's inequalities, things like, so some nice things happen there. Okay. So that gives you a lower bound that actually is quantitative. So for example, log of this gives you a lower bound on the number of equality queries that you need to make. Maybe let me mention some open problems. I'm already a little over time. I promise. So we showed this theorem that said if M reduces to equality, then M has bounded blocky norm. Is this an equivalence? So that's a nice open problem. So this is nice even if you care about, so if you think about this from these other norms that happen to be equivalent, so this is equivalent to the gamma 2 factorization norm, then that would kind of give you a structural theorem about matrices that have bounded gamma 2 norm. And blocky matrices happen to be the extremal case. So these are the only matrices that have blocky norm bounded by 1. So then that would, if this theorem happens to be true, then it's really cool. So it says that those extremal matrices explain why the gamma 2 norm or the blocky norm is bounded. And this problem is true for XOR matrices and grouplets. And this follows from Sanders', so these quantitative versions of the Cohen's idempotent theorem. So this follows from result and Greenham of Sanders and generalizations to other groups. But for now, let's think about XOR functions, which tells you that if the spectral norm is bounded, then you can write your Boolean function as a sum of, so if O1, then F is plus minus sum of indicators of cosets, or one many cosets. And if you try to lift cosets into matrices, they become blocky matrices, because these are just checking whether you're in the same coset, if x plus y is in the same coset. So this solves this problem. At least there's evidence that it might be true, but we just don't know how to prove it. Even like weaker versions of this problem are not known. So if blocky norm is small, is there a large monochromatic rectangle? Forget about like a complete structure or explanation for this.
Maybe you mentioned that it's equivalent to the rank, right? Blocky rank.
Yes. So this is also equivalent. To okay, so if you,
That's the question.
oh yeah, sorry. Yeah, this is so if it reduces, so if the blocky rank is bounded, then you can just query all of those blocky, the bounded many blocky matrices that appear in the expansion, and this direction we just showed in that theorem. Okay, so that those are equivalent. So again, because we didn't care about quantities, right? So there could be exponential gaps, etc., but we only care about constant cost. And as I mentioned, there's these approximate versions of these structure questions that are open in the open problem session I mentioned. So you can ask such questions for matrices that are Boolean. Maybe their blocky norm is not small, but they're in the L infinity norm, and they're approximated by a matrix that has small blocky norm. So do you have, can we at least say that they have large monochromatic rectangles or not? So that's also an open problem. And that would be equivalent to proving that matrices that have constant cost protocols that have large monochromatic rectangles, right? Large submatrices that are all 0 or all 1. So I'll stop here, sorry.